Let's start with a review of the right-hand rule. Whenever we have a moving positive charge, we said we use the thumb for the velocity of the positive charge or for the direction of the current. The fingers along the direction of B, then the force is the way the palm is going to push. Now, if it is a negative charge, we use the opposite direction than the direction of V. Now, for example, what we have here in the picture, I have positive charges moving towards the right. We have the magnetic field is upward parallel to the page. So fingers are pointing up parallel to the page. Thumb is pointing towards the right. Then the palm, using the right hand, is going to point out of the page perpendicular to the screen. The other right-hand rule is the magnetic field produced by a moving charge. So the first one is going to help us to find the force on moving charges. The second one is going to help us to figure out the magnetic field due to moving charges. And again, the thumb here, we put it in the direction of the current, or V if it is a moving positive charge. Then the fingers curl along the direction of B as we wrap our hand around the wire that's carrying the current. Okay, now let's consider this question here. We have a bar made out of metal. Metal, or in other words, conductor. Meaning that the negative charges are going to be able to freely wander around in that conductor. And we are going to move that conductor at a velocity v towards the right. Which of the following statements is true? Positive charges accumulate at the top of the bar, negative charges at the bottom. Since there is no complete circuit, no charge accumulates at the bar's ends. Or the opposite of answer 1, negative charges accumulate at the top, positive charges at the bottom. Okay, the answer is here really at the picture, but the color might give you the answer or it might not. But let's take the blue charge here, for example. The velocity is moving towards the right. So the thumb is moving towards the right, is pointing towards the right. Now the magnetic field in this case, we see here the points represented the magnetic field. So it's pointing perpendicular to the page towards us. So the fingers are going to point towards us. Now, if that's the right hand, if blue is a positive charge, then the force that's given by this expression on positive charges is going to point downwards, meaning in this direction. So that charge is going to feel a force in this direction and move towards the bottom like we see it here. So the blue here is representing for us a positive charge. If it were a negative charge, for velocity I use the opposite direction. So then my thumb is going to point that way. My fingers are still going to point outwards. So the force is up. And we see our charges being pushed upwards. So if my positive charges are going to be pushed downwards, negative charges are going to be pushed upwards, then that tells us we are going to have negative charges accumulating at the top, positive charges accumulating at the bottom. Now, If we have accumulations of charges, that leads us to think that the bar is going to act like a battery. So we need to determine what's the current that's going to be due to a moving bar, what's the direction of the current, and this is an additional thing. If there is any magnetic force, what's the direction of the magnetic force? To do that, let's, just to make sure we understand everything, let's go back to just a single positive charge moving towards the right. Now, because of the magnetic force acting on it, that's QVB sine theta. In this particular case, V and B are perpendicular to each other. Using the right-hand rule, thumb towards the right, fingers direction of the magnetic field, so they are going to be perpendicular to the page towards you. So the force is going to point down the direction of the palm. Now, if I have a bar, then as charges are going to move, there is a change in voltage, which is a change in electrical potential energy over charge. Change in electrical potential energy per unit charge. So what if we find the change in electrical potential energy by finding the work done on the charges as they are being moved towards the ends of the bar. So the work is force times D. Now what's the force? Like we just wrote it down on the previous screen, is QVB sine theta, with sine theta being equal to 1, since in this case V and B are perpendicular. So then my force is QVB sine theta. My distance, that's finding the work is going to take to move a positive charge from here to here, that's going to be L. And this is my Q. Now using this as 1, Q's cancel out. I end up having the EMF being VBL. The EMF stands for the voltage, the electromotive force, the voltage between the ends of the bar. We can show that it's going to take the same amount of energy to move a negative charge from here, from the bottom to the top, same kind of thing. But this is the bottom line. The EMF is V, the velocity of the bar, times the magnetic field, times the length of the bar. Now, let's think of something else. We are going to have a force on that bar. Why are we going to have a force? Or let me go back here. Now, as the charges move, I have a current within the bar. And remember from the magnetism chapter, whenever I have a current subject to a magnetic field, that bar is going to experience a magnetic force that's going to be IBL sine theta, where I is the current, B the magnetic field, L the length of the bar, and sine theta is the angle between I and B. So here, because of the motion of that bar, I'm going to have a current in that bar. Now we are completing the circuit so we can have, instead of just a pileup of charge, we are going to have a current flow and a light bulb lighten up. So I'm going to have a magnetic force on that bar. Now, from what we just have found out, the positive charges are being pushed downwards. That means the direction of the current is downwards. Which means that the magnetic force due to the current, I'm going to use the right-hand rule, the magnetic force that's given by IBL sine theta, using the right-hand rule, thumb is towards the bottom of the page, fingers perpendicular to the page towards you, towards the person looking at the screen, then my magnetic force is like this green arrow here, is pointing this way, which says I'm going to have a force that's going to try to slow down the bar. So to keep the bar moving towards the right, we need to supply a force in the opposite direction, which is going to be, we need to supply a force pushing it towards the right to compensate for this force, to balance this force. Now, the moving bar acts like a battery. The EMF, like we found a little while ago, okay, let's see, like we found here, is VBL. That's my EMF, sorry. Now, to find the current in the circuit, we can use Ohm's law. If, for example, my light bulb has a resistance R, I is going to be E over R, so it's VBL over R. The direction of the current, using the right-hand rule like I used here to see the direction of motion of the charges, you notice that these charges were being pushed downwards, positive charges were being pushed downwards, so that means the current is going to point in this direction. So it is clockwise in this case. Now the direction of the force, the magnetic force due to the magnetic field on the bar, it is towards the left. It tries to slow down the bar. Now what's going to be different if B is into the page instead of out of the page? If it is into the page, the magnetic force on the charges is going to point up. But the current is going to be in the counterclockwise direction due to this. Now, if the current is going to be in the counterclockwise direction, the EMF, of course, is given by the same expression. The direction of the force, using the right-hand rule, current up, magnetic field is towards the page, so the magnetic force is still in this direction, still trying to slow down the bar.